Hi everyone, sorry I couldn't be there today. Unfortunately we had to take my baby back into hospital last night, so apologies for not being there. I just thought I'd make this video this morning for today's lesson. Today we start the standard model, and this is our final topic, so we're almost there. We've got like a couple more lessons of content, and then we are finished. We have done all the physics that we can possibly do, and then we can start all the revision process, go back through everything we've done. Hopefully you guys are already working your way through those revision timetables from the revision guidebooks, which are a fantastic way to prepare for the end of year exam, as well as great revision for that test that we've got coming up in week 10 as our final end of topic test. So a couple of things on this topic. Firstly, it is possibly the most confusing slash hard to grasp concept that we cover, mainly because there's a lot of words, there's a lot of terms. It's very sort of I don't like to use the term, but very sort of biology based, where it's not like a lot of our physics where we have just a formula and you have some basic understanding of how to use it, where to get the information from, plug and chug, get a result. This is very much like there's just a lot of words, you need to know them, you need to know what they do, how to balance their charges, etc. So this will make more sense. But what I want you to do is, as we go through this module, so for today's lesson and in the next couple of lessons, I want you to build a mind map. So if you can remember, hopefully this is going to work. This is the ones that I made for other lessons, where I basically gave you a summary of the lesson on the board, and I've drawn all my arrows to say, like, well, in a very simple context, we excite heat or electrify gas, we get an emission spectrum, blah, 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 and we follow it through. So what I want you to do is create one of these as we go for the standard model, because there's going to be a lot of terms that will spit out, things that you can add on, etc. It doesn't have to be super pretty, and you're probably going to need more space than you originally assigned, so you may restart and do it a couple of times, but this is a fantastic way to get your head around this concept, link all of these concepts together for things like the bosons, the quarks, etc. when we go through them. So as you watch this video and in the next couple of lessons, please, please, please start building this mind map concept, and this is a great revision tool. So that's one thing I want you to do, and just add to it as we go. The next thing is there is a document, if I go to our class, there's this link here for advice for the standard model. So that's just a Word document here. This is something that SACE released, as the standard model was new not last year, the year before, 2 years ago, was the first year that they introduced this standard model, because it's considered like new physics, so they thought they'd add it. This is a great document to have a read through, both at the start and then the finish of the standard model topic, because it kind of summarizes what you're actually expected to know. The standard model has a lot of stuff, but there are some things in there that they're not going to actually assess, and so it's really good to have a look here and look at the conceptual understanding, and this is a bit more specific on what exactly are they going to ask you, and they even give you some questions. So these are sample questions straight from SACE on the kind of things that they're likely to ask. So 4 fundamental particles, etc., which we're going to talk about today. But this is a great tool to get your head around, oh man, there's so much information in this standard model. What actually do I need to know? This is a great document to have a look at, as well as, obviously, when we look at some practice questions. But given that this has only been out for 2 years, there aren't a lot of past exam questions on it, because there's only 2 exams that they've done so far, and we don't have the latest one with solutions yet. So let's get into it. Oops. All right. Okay. So standard model, part 1. So this is the final section of our physics course. This is the last module, standard model. So what it's about, the science understanding for today is that there are 3 fundamental types of particles. This thing called gauge bosons, leptons, and quarks. The standard model identifies fundamental forces, and gauge bosons are particles which mediate these forces. So the gauge boson for each force we'll talk about, and describe these fundamental forces and how they work and what actually causes them. So the whole reason we do this is because that scientists have developed this new theory known as the Standard Model. And it explains what the world is and what holds it together. So this is ultimately one of the really powerful things about physics, is this is where it explains everything in the world in one kind of basic model. It summarizes the whole thing. It explains all of these hundreds of different particles we know and the interactions, the complex way in which they do things. Before that, we kind of had some theories of, well, how does gravity actually work? It's not a physical thing. Same with magnetism and stuff like that. People often say, well, how does a magnet work? And we can explain what we've done so far in electromagnetism, but then beyond that, why is it actually attracted? What is physically going on there? There has to be some physical thing. And this is where the Standard Model comes in. So it describes something called fundamental forces and fundamental particles. And these two things are really important. So anything that I put in red throughout this lesson is something that you definitely need to know. So fundamental forces and fundamental particles we're going to cover. So far, we're familiar and we've pretty much dealt with the fact that all matter is made up of an atom. And then we've talked about those subatomic particles being protons, neutrons, and electrons. And we kind of said they're the smallest thing possible. There are the protons, neutrons, electrons that make up an atom, and that's it. And we hinted on the fact that there are some smaller things, particularly last year in the radiation topic. We talked about these things called neutrinos and antineutrinos as these like subatomic particles, but we didn't really deal in them in much detail. So a subatomic particle is a particle that is smaller than the atom. So protons, neutrons, and electrons are still subatomic, but they're the more common one. And we originally said there is nothing smaller, which we later found out wasn't true. When we built the particle accelerator, we were able to accelerate a proton and electron to very, very high kinetic energies. Using those concepts that we've talked about, similar to the cyclotron, we create a strong magnetic field to trap it off the walls so it doesn't have any resistance, it doesn't transfer heat. And then we can use these electric or magnetic fields to accelerate it at really, really high speeds around a tunnel. And then we can smash them into each other. And when we smashed them into each other, we actually saw, and I say saw, we measured that new particles were actually being created, or we were discovering these new particles. And this is where the Standard Model came, because we didn't have any way to explain what these things were or how they came about prior to the particle accelerators. And so the Standard Model explained these new particles that we discovered. So it suggests that there are three fundamental types of particles in the Standard Model. There are bosons, which are the exchange particles, and they mediate the fundamental forces that we'll talk about. There are leptons, and there are 6 types plus their antiparticles. So everything has a type and then an antitype or an antiparticle to it, which we'll go through. And then there are the quarks. So there's 6 types of quarks plus the antiparticles to that as well. So if you know what the quarks are and what the leptons are, and we'll cover that in the next lesson, once you've learned that, you just know the antiparticle to it. So we'll talk about that as well. But as long as you know what the 6s are, you can easily identify what the anti is. So a fundamental particle is defined as one which has no known substructure. So it is the smallest possible particle of its type. Whereas before we thought the proton, electron, and neutron were fundamental, we later found out that's not the case. These things are the smallest known substructure of anything. So the bosons, leptons, quarks are what make everything up above that. There are a whole range of different representations of all these particles, and looking at them can be quite confusing, particularly because we haven't even talked about the quarks, leptons, and gauge bosons yet, what all these crazy numbers mean, which is actually their spins and charges. Again, we haven't talked about it, so it's going to be a bit overwhelming. And there's a lot of representations. You can see things like this, or alternatively some sort of a table version. There are a whole range of different representations on how you can look at this. Once we've covered the topic, some of these you might find quite useful for revision, but for now I want to stick with our mind map system because it's you writing it down in a step-by-step process. But these are just some of the representations. So these fundamental forces that I talked about, there are 4 of them, and this is what the Standard Model is linking to. The 4 fundamental forces are electromagnetic force, the weak nuclear force, the strong nuclear force, and the gravitational force, which is just gravity. So these four are the fundamentals. There is no force that is smaller or makes up these. These are the four forces that contribute to every other force in existence. So let's have a look at each of them and some of its properties. The first one is the gravitational force. So we've talked about this quite a lot throughout physics. This is one of the most common. It's a mutual force between masses. So anything with mass has gravity. It's always attractive. You can't have repulsive gravitational force. For those of you that have seen the movie Interstellar, that was what they were trying to do. They were trying to find this anti-gravity thing to lift that monster space station off of Earth. Gravity acts over a range, but the magnitude decreases with the square of the distance between the masses. And we talked about that within the satellite gravitational topic as well. We looked at that relationship. Then we've got the electromagnetic force, which again is a mutual force between charges instead of mass. It can be attractive or repulsive. It acts over an infinite range, but the magnitude decreases with the square of the distance again between charges. So it's really the analogy or analogous to gravitational, except everything mass is changed to charge. And in this case, we can be attractive or repulsive, because gravity is always attractive. Then we have the weak nuclear force. So this is the force responsible for beta decay and any interaction involving a quark type, which will make more sense later. It acts on leptons and quarks, and it acts over a very, very short range. So we're talking less than 10 to the negative 18 meters, which is tiny. So again, almost similar in that it acts on leptons and quarks instead of charge and mass. In this case, it's a short range, and specifically it's responsible for beta decay and interactions between these quark types. Then we've got the strong nuclear. So this is a bit more common. This is the one that we talked about last year. This is the thing that binds the protons and the neutrons, which we'll later find out are actually hadrons. It binds them together in the atom, as well as binding quarks together. The strong nuclear can be attractive or repulsive. It acts on these hadrons and quarks, and again, very, very short range. Not quite as much as the weak nuclear, but still 10 to the negative 15 meters. So now let's look at some gauge bosons. The standard model suggests that the fundamental particles arise by an exchange particle called a gauge boson. It's basically the physical thing or the particle that is responsible for the fundamental force. So we say that these fundamental forces that we talked about before are actually caused by some particle interaction, which is kind of what I said right at the start of the lesson. There has to be something physically going on to do this. It's not magic, even though we say it's like non-contact forces and action at a distance. There is still something being exchanged between them. And that thing being exchanged is the gauge boson. So these are the gauge bosons responsible for the fundamental forces. So the electromagnetic force, the actual particle, the gauge boson that is responsible for it, is the photon. The weak nuclear force is the W and Z gauge boson. It doesn't have a fancy name, it's just called the W and Z gauge boson. Strong nuclear force is the gluon, which kind of makes sense in a way. It's almost a ironic name. It glues the protons and neutrons together in the nucleus, so we call it the gluon. And we have the graviton, which again, not particularly creative, is the particle fundamental to gravitational force. We haven't yet discovered this, so this is the weird thing. Based on everything else above, we say there must be this particle that we call the graviton, but as yet we haven't been able to actually observe it or discover it. So theoretically it exists, but this is one of the things of physics. It matches our theories, but we haven't yet discovered. So something maybe to aspire to in your lifetime, discover the graviton. So think of it this way. If we had two skaters and they're facing each other holding pillows, I'm not exactly sure why it's pillows, but this is the example that they use. So there's two possible situations here. Both skaters can grab the pillows from one another, and at the same time, as a result of this, by Newton's third law, it'll pull them towards each other. So it pulls them closer. So grab the pillows, pull it towards you, both particles end up closer. This is an attractive force. So this is the concept here, that if they're grabbing one another, they're being attracted together. The other option is that the two skaters could throw their pillows towards each other, And again, Newton's third law pushes them apart. And this is the analogy to a repulsive force. So throwing the pillows pushes away, grabbing each other's pillows pulls them towards each other. The electromagnetic force of attraction and repulsion between charges is explained through the exchange of the photon. So the photon is that particle responsible. It's the exchange particle. If you consider two electrons that are repelling each other, a photon is emitted by one electron, which is just like that pillow we talked about before. It's thrown a pillow at the other photon, or at the electron, which causes it to recoil as it transfers energy and momentum to the other electron. So we take these two electrons, they're pushing each other apart, but what's actually happening is at a subatomic level, the electron is throwing a little photon pillow at the other one, and by the third law, it's pushing it away. So that's causing that repulsion. The second electron does the same thing. It emits a photon, it throws its pillow, and it recoils. The more energetic photons are exchanged when they're close together. So just like if you think of throwing a pillow, if you're standing at point blank and someone hits you in the face with a pillow, it's going to push you away much, much harder. Whereas the further you are away, the slower those photon pillows are traveling, and the attraction or repulsion force is much less. So this is why it drops off. This exchange is occurring pretty much instantaneously. So even though we're picturing like this pillow flying through the air and hitting you and pushing you away, this is happening instantaneously. These photons are not visible. These aren't the same photons we're talking about in light. You're not seeing tiny bits of light shooting between electrons. These are called virtual photons. So these are invisible photons. Then we look at the weak nuclear force. So when a neutrino interacts, the mediators are called these exchange bosons. So W and Z exchange bosons are those weak nuclear force mediators that we talked about earlier when we talked about all those fundamental forces and their particle. Their existence was predicted in the 1960s, but it wasn't discovered until 1983. So this is a bit like that graviton we said. We haven't yet discovered it, but its existence is predicted. It may only be a matter of time before we do discover it and confirm that, just like we did with the W and Z boson. The W plus boson has a charge of +1e, so it's the positive electron. The W minus has a charge of -1e, so the charge of an electron. The Z0 is electrically neutral. So basically within those two exchange particles, we've got a W plus and minus, and we've got a Z0, which is just neutral. Then we go to the strong nuclear force. The strong nuclear force explains why those nucleons are held together, despite the fact that the protons are repelling each other and the neutrons are doing nothing. So you need something going on here to actually keep them together, and strong nuclear force is what does that. So this is due to the exchange of particles called pions, which is short for pi mesons, but we just call them pions. So these pions are the exchange particle within the strong nuclear force. This exchange particle is the gluon. So this is where it gets a little bit confusing. We're exchanging particles called pions, but the exchange particle itself is a gluon. So really we just talk about gluons as the exchange particle. So in general, the force between these nucleons is due to the exchange of the pions that we talked about up here, but it's actually the gluons that are exchanging between the pions and the nucleons that mediate the force. So that's a bit of a mouthful. But really when we're talking about what is the actual fundamental particle responsible for that force, we talk about the gluon. So the pion is the thing that's being exchanged, but it's the gluons that are exchanging between these pions and the nucleons that are actually mediating the force. So yeah, that's a lot to take in. Gravitational force. This is, again, one of the most common ones. We talk about gravity throughout all of physics. It's our bread and butter. The carrier of the gravitational force is the graviton. So as I said before, it's not yet discovered. The force is an inverse square force with an infinite range. So again, drops off with distance, infinite range. That's pretty much it. So this concludes the lesson on the fundamental particles. Like I said, make a mind map on those pieces, write down the fundamental particles, what the fundamental particles are, a very brief, like, couple of word statement on the properties of each of those particles. So like I said, for electromagnetic, attractive or repulsive, drops off at the distance, infinite range, that kind of stuff. Gravity, again, between mass, not charge, attractive only, that kind of stuff. So come up with that, split it down into the pieces, talk about those exchange particles that we talked about, and go from there. So for this lesson, there is no, sure, I'll save it. There is no questions, because we've really only touched on the very introductory stuff. So we've talked about these fundamental particles here, the gauge boson and the interactions. One thing you can have a look at is, which is a great resource, there's a link here for Quizlet flashcards. So that's these things. So as we go through, some of these might not be relevant to you yet because we haven't covered it, but for example, what are the 4 fundamental forces in the universe? And you've got the strong, the weak nuclear, the electromagnetism, and graviton, or gravitation. So things like that. What is the name of the mediating particle for the strong nuclear force? It is the gluon. So these are great little flashcards for you to work through if you want some revision. And as we go through the course, I highly encourage you to keep checking on these. It's a great little way to summarize each lesson, be like, oh, what was the name of the mediating particle for the weak nuclear force? It was the W plus minus and the Z0 boson. So remember, plus E, minus E, neutrally charged. So great little revision tool there if you're into the flashcards. No questions for today. Questions will start next lesson when we look at leptons, quarks, and antiparticles. So go through those flashcards, work on your mind map, and I look forward to seeing you guys next lesson.